Okay, we're going to work on topic 2.2 today, which is properties of matter. I had you do that PhET simulation, and so this table essentially kind of summarizes what you should have gained from that sim in terms of what are some properties of solid, liquid, gases. So this will become more important later on, but we usually represent solid as a lowercase s inside a set of parentheses, liquid inside parentheses L, and inside parentheses lowercase g for gas. Like I said, that'll become more important later on. Particle diagrams, that'll be explained as I walk through the remaining part of the table, so feel free to pause the video at any time. So what you should have discovered in your PhET simulation with solid is that those atoms, or if you're working with a compound, say water, is that they are in a definite shape and they're fixed. So if you were to pour table salt into your hand and look carefully at the crystals, you would see that they're all little cues. It doesn't matter if it's in the salt shaker or in the palm of your hand, it stays that shape. And then does it take the shape of in terms of its volume, we would say that its volume is also fixed, meaning its volume doesn't change how much shape it takes up, where it's placed or where it's at. Liquids, this starts to change. And so for volume and shape, and we'll start with shape, is it takes the shape of the container. Imagine when you pour yourself a glass of milk, as the milk is transferred from the jug to the glass itself, is it conforms from one shape to another, and that's because of the particle arrangement. You start to have more space versus what you saw in the solid. That's why it's able to conform. And then in terms of volume, it's definite or fixed. So if you pour 1 gallon of milk completely out into, say, a pitcher, it's still going to have that same volume of 1 gallon. So for gas, because those particles are so spaced out, that it takes the shape of its container. Meaning, if you spray perfume or some kind of Febreze, for example, in one corner of the room, eventually somebody on the opposite side of the room can smell it. And that's because those fragrance molecules are arranging itself to fill the room. So the volume is going to change so it can expand or contract. And in this case, if you're spraying something in a room, it's definitely expanding out. And that's because there's all that empty space between gas molecules or gas atoms. And so then again, it's taking the shape of the room. And so it's then taking the shape of the container. So the distance between them, that's one of the key things that gives us these properties. And so a solid, you have the smallest amount of distance. There's a medium amount of spacing in a liquid, and then the gas is mainly empty space. There's lots and lots of space in between them. That's why you can take a balloon and compress it to a certain point, because you're just shrinking that amount of empty space between the atoms and molecules. So in terms of particle movement, because they are so packed together in a solid, we say that they are mostly fixed or they vibrate in place. And that's what the little kind of parenthesis-like things are trying to represent in the diagram up above. Liquids, they have limited motion, so more motion than a solid, but not as much motion as a gas. And then gas molecules are essentially free to move without really any worries about what everything else is doing around it. If it collides with something, it just changes its direction of motion. So because solid particles are so packed together, that's going to have the most amount of attraction between them. Liquids, it starts to weaken, and then gas molecules have the weakest amount of attraction. Like I said, if it collides with one another, it will just essentially send it into another direction. And again, it will continue to move in that kind of chaotic pattern. So we're going to work on identifying today physical versus chemical properties of matter. So we learned how to classify it last week, and now we're going to start to work on how can we describe it. Physical properties are ways of describing matter. So you can use your 5 senses to identify a physical property. You can measure things like its height, its weight, its temperature. Understanding what state of matter it is helps decide again, physical properties. And so typically when we look at physical properties, you're essentially describing it. So I kind of think of these as adjectives of a material. Physical properties are useful because we can use those to help decide where something might be useful, knowing to use a metal for wiring versus a non-metal, those types of things. So these have a lot of implications in designing materials. Here's a list up top of a bunch of different physical properties. So I talked a little bit about the first few. Texture can be useful depending on what you're working with. So melting point and boiling point, what we mean by that is what temperature something melts at versus what temperature it boils at. So water has a melting point of 0 degrees Celsius or 32 degrees Fahrenheit. And for example, boiling point of water is 100 degrees Celsius. Luster is the ability to reflect light. So metals tend to have a high luster or they reflect light very well versus non-metals do not. And so then we have a list that we're going to fill out with some terminology that you're maybe not as familiar with. So the first two talk about ability to transfer, and one is heat and the other is electricity. So let me get my pen here and let's change the ink color. So the ability to transfer electricity or heat, we're just going to call those conductivity. So the ability for something to dissolve is called solubility. You know that salt will dissolve in water, so we can say that salt is soluble in water. Sugar will not dissolve in gasoline, so we can say that sugar is insoluble in water. So even if it's the opposite of it, it's still describing a physical property. Liquid thickness, that's called viscosity. If you have a cup of, say, water and a cup of honey, you know that if you pour them, the water will empty more quickly than the honey because water has a lower viscosity. Honey is very viscous, meaning it has a high resistance to flow. The ability to fold into sheets is malleability. So essentially, can you form it? And a lot of you guys used aluminum foil in your videos. So aluminum is a malleable material, which makes it great for using for aluminum foil. Brittleness is the tendency for breaking or cracking. If light can pass through it, is transparency. Can you change the shape of it without it breaking? Flexibility. Can you make a wire out of it? It's called ductility, or if it's ductile. So some of you use copper wiring, for example, in your videos. So copper is a really good material for forming wires from, so we can say it's ductile. And then can it be attracted to a magnetic field is magnetism. So this is a general list of physical properties that we can use to describe matter. This by no means is the only list. There's more material or more examples out there, I should say. Now the next thing is we can subcategorize physical properties into these two types called intensive or extensive. And essentially what these break down into is, doesn't matter how much of the material you have or not. Because like I said, we can use physical properties for deciding what to use it for, but also if you're given something and you're not sure what it is, you can then use these physical properties to identify an unknown material. So an intensive property is based on the identity. So I have an easy way to remember this. Intensive starts with I, identity starts with I. So it does not matter how much of the material you have. This is a property that stays the same with the material, whether you have a gram of it or you have a kilogram of it, for example. An extensive property is a property of a material that changes based on how much of it you have. So when we look at these four examples here, what I'm looking at is if I cut something in half, does this property change or not? So I'm going to use a penny as my example. So if I have a penny and I cut it in half, will the mass change? Yes, the mass will change in that half. And so that is an extensive property. Quantity matters. If you cut that penny in half, does the color change? No. Copper has that distinct color. That's an intensive property. Ductility, it doesn't matter how much copper you have, it has that property to be formed into wire. So that's, again, an intensive property that all copper has, no matter on quantity. Now, let's say you have a copper wire. If you cut it in half, does the length change? Yes, so quantity does matter there. So that's extensive. Melting point, and this is a common misconception. So we're going to use water here. So if you have an ice cube or a whole glacier, it does not matter. It all melts at the same temperature, 0 degrees Celsius. Now, the amount of heat that it takes to melt it is different, but we're talking about what temperature something melts at. So it doesn't matter how much you have, therefore, this is intensive. Finally, the volume, the amount of space it takes up, that is something that changes based on the quantity that you have. So that's an extensive property. So again, think intensive is identity, eye for an eye. Extensive is based on quantity. Chemical properties are essentially ways of describing how it can behave chemically. So we're not changing anything about the material. What we're doing here is describing its behaviors. So here's a list of some 5 general chemical properties. So if we want to describe the ability of something to burn, that's called flammability. So a lot of times on big semis, if you take a look at the back, they usually have the diamond, MSDS diamond, to talk about its properties. And if they are hauling, say, gas to a convenience store, those types of things, it'll have a flammability rating based on what they are hauling. The ability to lose luster as a result to exposure to air or moisture, that's tarnishing. The Statue of Liberty is a very good example of tarnishing taking place. All of that green layer that we see on it is that tarnish. The ability to decay, that's decomposition. So you may be thinking of it from a biology aspect. There's also a chemistry aspect. So we're not just talking about organisms decaying, but we're talking about a compound decaying or breaking down. And we'll talk about that more later on as the year goes on. The ability to rust is oxidation with oxygen. So if you had a rusty object around your house, you could have used that as a compound in your video that it was iron 3 oxide, and that's where iron has come in contact with oxygen in the atmosphere to form something new. So we know that iron is highly susceptible to rusting. So it oxidizes very easily with oxygen. And then the ability to form a new substance after mixing with other chemicals, that's reactivity. So sodium, if you put it in water, it's going to go boom. It's very reactive with water. And so that is describing that it's very reactive. Now, on the same token, you could say if you put aluminum in water, that it is non-reactive. That is still describing a chemical property. So even if it's not going to produce or allow for something to change in terms of describing that, it's still looking at how it can behave. And again, by not doing something is also describing a behavior. So here's a list real quick where we're going to identify if something is going to be chemical or physical. So again, physical, think of it as it's describing the material. Chemical is describing how it could potentially change. So sugar is soluble in water. So when you dissolve anything, it's still that same original material. If you've ever made rock candy, or if you boil a pot of water that, say, has salt in it, if you let all of that water disappear, that salt or even the sugar would still be there. It would be left behind. So solubility is the ability to dissolve. So we are describing a physical property. Oxygen is an odorless gas, so we're describing a property about it, and so that's physical. Sodium reacts easily with other elements, so we're describing how it can chemically behave, so that's a chemical property. Conducting heat and electricity is a physical property. Water boiling at 100 degrees Celsius, that's a physical property. And finally, oxygen is flammable, so we're describing how it can behave to produce a change, and that's a chemical property. Now, I know it says if it's an intensive, or excuse me, if it's a physical property, identify as intensive or extensive. So again, this is based on that identity or quantity. So I did a poor job in selecting my physical properties here. All of these are intensive. What I mean by that is that it doesn't matter in terms of quantity. Sugar can dissolve in water, so that's an intensive property. Doesn't matter how much oxygen gas you have, it is still going to be odorless. Doesn't matter how much copper you have, it will conduct heat and electricity. And going back to my ice cube versus glacier scenario, doesn't matter, or I guess in this case we're talking liquid. I was talking about melting earlier, but it doesn't matter how much water you have, it's going to boil at the same temperature. So again, if you wanted a physical property that was an extensive example, you could say that copper has a mass of 10 grams. So you're describing something about it. And again, because it's a quantity, you could use that as an extensive property. So that's what your homework is going to work on today. Please reach out to me if you have any questions.